welcome to the course Advanced Reaction Engineering. So, we already have started discussion on bioreactors. So, in the bioreactors various type of phases are there, means when we conduct any bioreactions, means reactions biomass and substrate reactions to formations of the new cells as well as product formations is there. So, in that case you know that is the basic reactions for any bioreactions in a bioreactor. So, that for this particular reactions in the left hand side you have to use cell to start the reactions, new cell initially few quantity of small amount of the cells you have to put inside of the reactors, and then substrate you have to charged, you have to maintain particular temperature, pressures or other pH, everything so you have to maintain, and then we start the reactions. So, then more cell formations would be there. At the same time that product formations is there, that substrate will convert it into the product that we know. So, here the if we notice about the components in the reactions or the cells. So, mass balance if you want to do, then there is component cell is there, substrate is there, and number third is the product. So, these are the three components is there inside of a bioreactor. So, once we do the material balance for these components, means once the reactions which take place in this type of bioreactor. So, what would be the concentration of the cells, what would be the concentration of the substrate, what would be the concentration of the product at different times. So, not only that this type of reactions is not very simple. So, if we want to know individual component concentration, means cell concentration, substrate concentration, product concentration. So, overall things we have to do the material balance, or theoretically how we can find out that. So, let us say this type of in a flow reaction or flow systems is there. So, here maybe that substrate as well as cells that we are feeding in the reactor is V0 dm³ per second at a volumetric flow rates we are passing inside of the reactor. This is a reactors, it is a CSTR reactors, that is was taken for here. So, in this reactors initial substrate concentration is this, initial cell concentration is this in the feed line, that is entered inside of this particular reactors. Here we are maintaining temperature, pressure and pH, reactions will conduct, and stirring is also there. So, then cell will be forms new cell, substrate will be converted into the product as well as new cell formations would be there. So, that outcomes of product that is come out from the cell or the reactor, that would be the substrate concentration, initially it was this, and cell concentration would be this, initially cell concentration was low, but finally once it is come out from that reactor, that cell concentration would be Cc, and volumetric flow rate is this. If there is volume changes, then V would be different. If there is no volume changes, then V naught equals to V. For liquid phase reactions, most of the cases we do not consider volume changes, there is very rare volume changes is there, and V is the total volume of the reactors. Okay. So, here when we are going to do the mass balance. So, here in the mass balance means growth of the microorganism that we have to count, and that counting that is based on number of living cell or maybe mass of the living cells, number of living cells or mass of the living cells. So, if we do the material balance for cells, means that is initially we are feeding here, then new cell formation is there, and then finally the cells is coming out. If there is accumulations or not, if there is accumulation part is there, so then that also we have to count with time, progress of the times. So, here this is the cell balance, means one component, here three component is there, mass balance for cells, mass balance for substrate, mass balance of the product, mass balance of the cells, mass balance of the substrate and mass balance of the product. So, these are the three components. So, first we will do the mass balance for, or we will develop some equations for cells, then substrate, then product, one by one we are going to discuss. So, first if you consider the cells, rate of the cells entering per gram per second, net rate of generation of the living cells, net rate of generation of the living cells inside of that reactors due to the cell reactions, and rate of the cells leaving. So, from the reactors outlet or output is there, the rate of the cells leaving from the reactor, that is gram per second, and rate of accumulation of the cells in the reactor. So, this way we can write that is the cell balance or mass balance of the cells with respect to the cells only, not other component we are considering, only the component that is the cell presence with respect to the cells we are doing. Then we will do the substrate, then product. So, V naught Cc naught, that is the gram per second, that is the cell entering, this is Rg minus Rd into V. Rg is the rate of cell formations rate dCc by dt, and minus Rd, that is the rate of cell decay or cell dead is there. So, that part we have to subtract. So, per unit volume basis we have multiplied with that with volume, okay. And then rate of the cells leaving from the outlet dCc small v into Cc, volumetric flow rate we know, and concentration of the cells we know. So, then if we multiply volumetric flow rate with the concentration of the cells, then gram per second of the cells leaving from the reactors we can find out, and rate of accumulation, that is the V into dCc by dt. So, this is the equation 1, and for cells similarly for substrate also we can do the material balance, rate of the substrate entering here, and then substrate will consume or react or disappearance in the cell reactions, substrate remaining or lefting, that part will leave from the reactors. This is final substrate concentration, this is initial substrate concentration. So, initial substrate concentration would be high, and finally the substrate concentration would be low as the progress of the cell reactions. So, then rate of the substrate entering equals to this, rate of generations, rate of substrate means reactions if we know, or disappearance, and multiplied with the volume. So, then net rate of generation of the substrate equals to this, and rate of substrate leaving from the reactor is this, and rate of accumulation of the substrate is similarly V into dCs by dt. So, here in the first equations, these equations if we consider it as a batch process, so then there is no volumetric flow rate. So, mass balance would be that, as that there is no inlet outlet. So, this part we can eliminate, this part means only this part and this part remaining there. So, for the batch systems, so we can write this V into dCc by dt equals to Rg into V minus Rd into V, okay. Or these equations if we dividing both side, left hand side and right hand side with respect to the V. So, then dCc by dt equals to Rg minus Rd. So, that is the cell disappearance equals to this, this way these equations we can write this, okay. So, now for the substrate for the substrate also the equation 2 we developed. So, similarly in case of the substrate also, initially for the batch system the amount of the concentration of the substrate that we have charged inside of the reactors. So, means initially and finally, since for the batch systems, so there is no in out. So, only rate of generations or disappearance of the substrate part, that part we can consider, and similarly for substrate accumulations we can write. So, here in these equations we can simplify, or we can write these equations equals to this, okay. So, equation 4 we can write this way, V into dCs by dt equals to Rs into V. Rs is the rate of substrate formations, okay. So, plus sign is there. So, that therefore, it is rate of formation of substrate, but in most of the cells reactions substrate disappears, okay. So, these equations substrate disappearance or reactions we can write minus Rs equals to yield coefficient, rate of formation of cells. Here in with respect to the rate of formation of the cells, that rate of substrate disappearance was written plus cell maintenance, okay. So, if this already equations we have derived in our previous class, so minus Rs we can substitute here, then the equations would becomes like this. So, yield coefficient, rate of cell formations and volumes and cell maintenance, the amount of the substrate being consumed, that way we can write the substrate balance equations this way, equation 5, okay. Or else we can divide both side, left side and right side in equation 5 by V, and after that if we simplify these equations, then equation is coming dCs by dt equals to YSC by into minus Rg minus MC, that is the rate of cell new cell formation, means substrate consumptions or disappearance, that is with respect to the cell concentration formations and cell maintenance, there also substrate disappearance or consumptions is there. Based on that we can write this is in the growth phase, phase 2. Okay. So, growth associated product formations we can write the substrate consumptions by these equations. Okay. So, this is for growth phase. So, there is in the third phase, that is the stationary phase. So, in the stationary phase we know this is the stationary phase. Okay, this stationary phase, here only product formations is there. So, substrate consumptions whatever that would come that is due to the cell maintenance and product formations. So, here the substrate balance we can write at this particular case, this is case 2, means substrate balance we are doing. Case 1, that is the growth phase, we have discussed this phase, phase 2. So, here's case 1, that is the growth phase. So, growth phase substrate concentrations we can write dCs by dt equals to YSC minus Rg minus MCC. So, these equations we have to use for this. Here's the rate of the substrate consumptions, and in the case of the third phase, that is the stationary phase, case 2, in that case the substrate balance we can write this way. Okay. So, here YSC means here this equation for substrate disappearance for case 2, and here in this case we can write this way, this is for stationary phase. Okay. So, V into dCs by dt YSP minus Rp into V minus MCC into V. So, Rp is the rate of product formations. So, here Rg is the rate of cell formations, here rate of product formations or rate of product disappearance. That way we can the same equations, this equation both are same, but here's rate of formation of new cells and here rate of product formations we have writings, and at the same time yield coefficients also in both the equation are the different, but in this is for stationary phases, rate of cell that substrate that is being consumed or rate of changes of the substrate from the mass balance for this bioreactors we have done. So, next is the rate of formation of the product. Rp is the rate of product formations related to the substrate consumptions. If we want to write V dCp by dt equals to Rp rate of product formations into V, that is the volume of the reactor of the system. So, now Rp we can write this way, means in terms of the substrate consumptions of change of the substrate, YPS, that is the yield of the product per unit substrate consumptions, and rate of substrate disappearance if you know. So, then if we multiply it with that volume, so then that changes of the product or formation of the product rate that we can find out. Okay. So, now equation 3, 5 and 7 we have to solve by using ordinary differential equation solver. These are the ordinary differential equation, first order equations. So, equation 3, this is the equation 3 for cell, equation 5 for the substrate, okay, and equation 7 that is the for product. So, 3 differential equations we have, these 3 equations we have to solve with respect to the ordinary differential equation solvers. So, then with respect to the times how the component concentration changes when cell, substrate and product concentration inside of the reactors during cell reactions inside of the bioreactor, that easily we can find out, okay, theoretically, or we can using these equations we can find out. So, here you can see, so this is the equation 3, this is equation 5, this is equation 7. So, these 3 equations simultaneously we have to use by equation ODE solvers, that is polymath is theirs or any other equations or solver is theirs that you can use. So, what are the parameters means component, known components are theirs, that components you have to supply and the results will come out, or after polynomial or ordinary different equation solver of these are the 3 equations. So, we can get x axis time, y axis concentration, that may be substrate concentration, then substrate concentration will gradually decrease, and product formation or product concentration that will gradually increase along with increasing the time, and cell concentration, that is with increasing time that cell concentration it would be like this. That is theoretically that way we can solve these three equations and we can find out the concentration of the individual component, that is product, cell, substrate, we can find out easily. So, now we will go for an example, that is the bacteria growth in a batch reactors. So, considering these are the equations, how we can find out these plots or concentrations, you can say concentration of the cells, concentration of the substrate, concentration of the product with respect to the times. So, how we can find out these are the data, means theoretical data we can find out based on experimental results, also we can validate also. Okay. So, these are the things we will discuss. So, here one examples we have taken, let us say glucose to ethanol product formations, Saccharomyces cerevisiae, this is the cells that was used for this particular conversions glucose to ethanol production. So, in this particular reactions, when we are conducting inside of a bioreactors, this particular reactions, initial cell concentration that was taken, that we have to charge inside of the reactor to initiate the reactions, that was 1 gram per dmq, and the substrate initially that we have charged 250 gram per dmq. That quantity of the substrate or initial concentration of the substrate that was placed inside of the reactors, and this particular reactions Cp star is given this. Okay. N is the some parameters, that value is given, mu max that is given, Kd is given, M is the given, that is the maintenance constant sum is there, M, that value is given, and yield coefficient cell substrate is given, product substrate is given, product and cell is given. So, these particular reactions, and also Monod constant, that is the case, that part also is given. So, these are the component or the data are given for this particular reactions. So, now we have to develop this. Okay. So, growth rate with respect to the times concentrations we have to find out, Rg rate of cell formations, rate of substrate consumptions, rate of cell dead, and with respect to the times that we have to find out. These tables we have to fill up. So, how that we can do for this particular reaction, that we will discuss. So, in the mass balance equations for the cell, substrate and products, these are the equations we already have derived or we have discussed in our we have discussed. So, these are the equations we have, okay. And few components are also there, that is additional data is given, and in the Monod equation for the bacterial cell growth rate, that is Rg equals to K observed mu max Cs Cs Cc by Ks plus Cs, and K observed equals to this. So, that we can substitute here. Okay. So, then the equations would become this. So, here K observed that is given, that is the constant sum, and Cp dot, that is the product concentration at which all metabolism ceases, means there is no maximum, that is the concentration of the product. So, after that concentration up to that means when it is reached the product concentration, so there is no further cell growth is there, means cell almost will die, means concentration that is the product concentration at which the all metabolism ceases, means there is no growth. So, N is the empirical constant. So, here it value is given, Cp star is also value is given, N value is 0.52, that is given. So, here's rate of the cell death, that is given Kd into Cc, Kd value is given, RSM, that is the substrate consumptions, rate of substrate consumption, that is given M into Cc, M value cell maintenance constant is utilization terms is also given, RSM, that is the rate of substrate consumption for the cell maintenance. Okay. So, these are the equations also would be useful to solve. Okay. Now, rate of the product formations to cell growth. So, Rg is the cell growth and Rp is the product formations. If you know yield coefficient, product and cells, so then if you multiply it with this, so then rate of product formations we can find out. If you know rate of product formations, cell growth rate we can find out. If you know Rg value, then if you multiply with this yield coefficient and we will get rate of product formation, either one we can find out. Okay. So, now combining all the equations that we have shown here, dCc by dt, that is equals to Rg minus Rd, that we can write this way, Rd equals to this, and rest of the part is Rg. Okay. And dCs by dt, that is equals to, we can write this way, and dCp by dt, that we can write in this way. Okay. So, now these are the three equations. Also these are the equations is also there, substrate concentrations or disappearance of the substrate, and rate of the cell death, that also Rd. If Kd value is given, if you know Cc value at different times, that we can put, then Rd value will come, substrate cell concentration if you know that at a particular times, that we can put it here, M value is given, then RSM value we can find out. So, rate of substrate disappearance or for the substrate consumptions for the cell maintenance, that we can find out. Okay. So, after solving this, these are the data given for this particular means reactions. So, then these results we can find out, or these results will be evaluated. Okay. Means that results will comes as a means ordinary difference, means these are the equations is there, 1, 2, 3, 4, 5 equations are there, and corresponding data are also given. Okay. All these are the data are given. So, yield coefficient is given, cell maintenance constant is given, cell death coefficient that is given, mu max given, n is given. So, these are the Cp dot is given, product concentrations, that is the maximum. So, P dot Cp star is given, Cp is not given, that we have to find out. So, now if we solve these 5 equations, this 1, 2, 3 and 4 and 5 by using ordinary differential equation solver. So, then we can get at different time 0, 1, 2, 3, 4 time hours corresponding cell concentrations at different times, we can find out once by putting all parameters, cell concentrations, substrate concentrations will get, and product concentrations by solving these equations we can get, and Rg rate of cell formations, that Rg is given, that equations if we solve. So, by putting Ks value is given, this value is given, Cp prime is star is given, mu max is given. So, substrate concentration, cell concentration and product concentration we have to put in these equations, then Rg value we can find out, RSM, that is the substrate concentration or disappearance. So, here if you know cell concentration at different times, so then RSM value also we can find out, or by solving these equations we can get Rd, that is the cell death in the after particular period of times, rate of cell disappearance or cell death. So, that also we can find out by using equation 4. There we have to put only the cell concentration, Kd value is given. So, then Rd value also we can find out. Okay. So, now this is the results, that is the output of solving these all 4, 5, 6, 7 6 equations. So, then you can plot with respect to the time x axis and other component in y axis. If we let us say concentration and rate time if we plot. So, y axis cell concentrations and x axis, that is the time. So, when cell reactions is there inside of the reactors, the substrate, that is glucose, that is being converted into the ethanols and new cell formation is there. So, that x axis time and y axis cell concentration, it would be nature would be like this, means new cell formations is there, the concentration of the cells initially was Cc 0, low concentrations, and it gradually increase with increasing times. Okay. So, that way cell concentrations gradually will with increasing times, the cell concentration gradually increase. Okay. Similarly, substrate concentration, that is Cs, that is the substrate concentration, initially we have taken large quantity of the substrate to start the reactions, and that substrate would be converted into corresponding products. So, substrate consumptions is there with increasing times, that would follow like this, and product formation is there, initially product Cp 0 was 0, no product was there, only new cell, few amount of the mass of the cells, and substrate was present inside of the reactor. So, then once reaction started, then new in the stationary phase, substrate formation is there. So, with increasing time product formations or ethanol formations is there, and substrate, that is the glucose, that is gradually decrease. So, the nature would be like this. Similarly, rate there are 3 different rate I said. So, Rg, Rd, Rsm, rate of cell formation, this is the Monod equation. So, Rg, there all parameters are knowns, only substrate concentrations and cell concentrations we have to put, cell and substrate cell concentrations and substrate concentration with respect to the times we know at different times what would be the substrate concentration and corresponding cell concentrations. If let us say this is 2 hours, this is also 2 hours. So, corresponding substrate concentration, cell concentration we know, then corresponding rate of formation of the new cells, Rg value also automatically with the ordinary differential equation solvers Rg value will come. If you plot Rg and T time with respect to the then rate of cell growth is theirs, then it would be down cell formations with further progress of the times, the rate of formation of the new cells that will downs. This is the optimum or maximum growth or cell formations is there. Similarly, the substrate consumptions, that is was like this, means with increasing progress of the times the substrate that was put inside of the reactor, it also gradually will decrease concentrations or rate of the substrate consumptions gram per dmq per unit times rate of disappearance of the substrate, that would be there, rate of disappearance of substrate, rate of formation of the cells, and rate of Rd, that is the rate of death cells, means after a certain period of times when cell growth will be stopped here, cell growth, and then cell death is there. So, then it gradually increase after a certain period of times. So, that also we can find out, and since rate of product formation is there, Rp also we can find, means concentration of the product is there, Rp also we can find out. So, for Rp equals to these equations is theirs, Rg into yield coefficient Yp by C. So, if you are able to find out y p by c, if you are able to find out, multiply it with Rg cell growth different times we know Rg rate of cell formations. So, then Rp also we can find out rate of product formations. Okay. So, maybe Rp is like this, Rp also we can find out, and K observed, that is the constant K observed, that is as a function of n, Cp star and Cp, concentration of the product with increasing times, that is gradually increases. So, Cp star is given, Cp star value is given 93 gram per dmq is given, n is value is also given, Cp star and n value is given, and once all equations will solve, Cp at a different times, concentration of the product 0 hour to 1 hour, 2 hour, 3 hour, 4 hours, individual times Cp we can find out 0, 1, 2, 3, these concentrations we can find out. So, this Cp we can put it here, n value we know, Cp star value we known, then K observed also that we can find out, and we can plot, then K observed value gradually decrease with increasing times. Okay. So, these are the means outcomes for that numerical problems, that is bacteria growth in a batch reactor. How to solve this means that we have discussed. So, here two things we have discussed, just I am summarizing. So, in the mass balance cell, substrate and product, mass balance we have done, and different mass balance, cell balance, substrate balance equations that we have derived, and for batch operations equation 3 for the cells, equation 5 for the substrate, and equation 6 for the equation 6 also substrate, and equation 7 is for product, changes of the product concentrations with respect to the times in the inside of the reactors that we have derived, and these are the equations we can solve for any bioreactions that is happening inside of a bioreactors. So, then concentrations of the individual component in terms of gram per dmq means or gram per second, also means rate of formations that we can find out. Okay. So, these are the concentration in individual gram per DMQ will come, and other things means rate parameters also will come out, and yield coefficients also for product with respect to the substrate, product with respect to the cells. That way also we can find out, and that if it is given we can put it and then we can solve it to find out different parameters or Monod equations or concentration with respect to the times. These are the equations we can solve. Okay. So, how to solve a biochemical reactions by considering all equations that we have discussed. This is the outcome or the results means for a bioreactions. Okay. So, that is our objective. So, if you are able to identify individual component that is present inside of the bioreactor, if we find out components as well as concentrations. So, then means sometimes there are so many reactions are there. So, where all components is not possible to find out. So, or validate means with the Monod equations means how the reactions bioreactions is proceeding, means the way rate other components changes are there inside of the reactor. If we want to know, then this way we have to find out or we have to validate with the experimental results. Okay. So, thank you. So, today is up to this. So, I think in the bioreactions, so different yield coefficients, bioreactions rate law, rate parameters, how to find out, that we have discussed. So, thank you so much. Okay, thank you. So, today is up to this.